Section 6.2 is on inverse functions and relations. An inverse relation is the set of ordered pairs obtained by exchanging the coordinates of each ordered pair. In other words, just switch x and y. So let's take a look at a really simple example here. Find the inverse of this relation, this set of ordered pairs. In order to do that, we basically just rewrite it and switch the x and y. So make sure you're using set notation. So instead of 6 comma 7, I'll have 7 comma 6. And instead of -3, 0, 0, -3. And instead of 4, -8, I'll have -8, 4. And that's the inverse of that relation. Now you can also have an inverse function, and that's an inverse relation that is actually a function, not just any random set of ordered pairs, but it meets all the criteria for a function. It is written in this way: f with a little -1 exponent, looks like a little exponent, and then the x in parentheses, and we say that the inverse of f of x. It's not f to the -1 power, it's not f -1, it's the inverse of f of x. So if one function f and f, okay, -1, inverse of f, are inverses, then f of a equals b if and only if the inverse of f of b is equal to a. You'll notice it switches basically the x and the y, the input and the output. If the inverse of a function is also a function, then it is one-to-one and passes both the vertical line test and a horizontal line test. So a couple things about that. You can have the inverse of a function not be a function, and we'll see an example of that when we graph it. But if it is a function, then it'll pass the vertical line test. Recall that from Algebra 1, where if you pass a vertical line over the graph of the function, it only crosses it at one place at a time. And it will also pass a horizontal line test, which is kind of the same idea but uses a horizontal line. So let's do a couple examples here. Let's find the inverse of each function and then graph the function and its inverse. And you'll probably recall some of this from Algebra 1, how to find the inverse of this function. So we have f of x equals 2x plus 4, and that's obviously a linear function. It's going to be the graph of a line. So let's find its inverse. So to do that, we replace f of x with y. And because the inverse flips the x and the y, we're going to exchange x and y. So I'm going to write this as x equals 2y plus 4. And now I will solve this for y. So subtracting 4 on both sides, and then dividing everything by 2. And I'm going to clean that up a little bit. So that's going to be y equals 1/2 x minus 2. And then let's write that in function notation using our inverse of the f of x notation, equals 1/2 x minus 2. So there's the inverse of 2x plus 4. So let's graph each one of those, and I'm going to have a little fun here and I'll graph them in different colors. So our original function is 4 and up to and right 1. This one's easy to graph because it's linear, and I can just do y equals mx plus b to graph it. Okay, so there's my original function. Let's graph its inverse. And my y-intercept is -2, and I'll go up 1 and right 2. And down 1 and left 2. They actually intersect at a point right there, which is kind of nice. And draw that line. So there's the graph of the original function and its inverse. Now here's a really interesting thing about a function and its inverse is they are reflections of each other across the line y equals x. So the line y equals x is this line that goes through 0, 0, 1, 1, 2, 2, and so forth. Okay, that's the line y equals x. And as you can see, if I were to take the pink line and reflect it over the green line, I would get the blue line. So that's just a really cool thing that's true about inverse function and its inverse. Let's take a look at a second example here. Here we have g of x equals x squared plus 4. So let's go ahead and do some algebra and come up with the inverse of that. So I have y equals x squared plus 4. Switch x and y. And then let's solve that for y. So subtracting 4 on both sides. And then I'll take the square root of both sides, so I'll get y equals plus or minus the square root of x minus 4. Okay? Now, actually, I am not going to write that in like g negative 1 notation, because this function right here, g of x, that's a parabola that's been translated up 4 units. So it's going to look like this. Okay, and as you can see, it is a function because it would pass a vertical line test, but it will not pass a horizontal line test, so its inverse is not a function. So when I go to graph this one here, that's going to be x equals, or y equals plus or minus, so that's going to be one above and one below. That's going to be the square root function that looks like this. That's the above part. And then the part below, because of the negative, you can see clearly that will not pass the vertical line test. So the inverse of the original function is not itself a function. But all they asked us to do in this case was to find the inverse and graph it. Okay, here's another cool thing to look at. Two functions are inverses of each other if and only if both of their compositions are the identity function. So that means if I do f of g of x and that equals x, and g of f of x equals x, then g of x and f of x are inverses of each other, which is actually kind of cool. So let's take a look at a couple examples of that. So we need to determine whether each pair of functions are inverses. So I need to find f of g of x and see if that's equal to x, and g of f of x and see if that's equal to x. So remember, we have this little notation that kind of looks like fog, but it really isn't. And what that basically means is I have, let me try this, f of g of x. So what I'm doing is I'm putting g into f. So let's do that right now. So take this function g and put it into f for x. So that's going to give me 3 times 1/3 x plus 4, and then minus 3. So that's 3x, and I'm putting g of x in for x minus 3. Let's simplify that and see what we get. So 3 times 1/3 is x, plus 4/3 minus 3. Oh, I'm sorry, not 4/3, my mistake. Plus 12 minus 3, and that gives me x plus 9. That is not equal to x. Remember up here we said that f of g of x, both of the compositions have to equal x. That does not equal x, so no, these are not inverses of each other. And in fact, I don't even have to do the other one because they both have to equal x. I don't have to do g of f of x for this one. Let's try another example here. Here I have f of x equals 2x squared minus 1, and g of x equals the square root of x plus 1 divided by 2. So let's start by doing f of g of x. And I like to write it like this. It helps me to see it better. It really actually looks like g is in f, so that makes a little more sense to me. So 2 times this, the square root of x plus 1 over 2, and that thing's squared minus 1. Now that looks kind of gnarly, but don't worry about it. It's really not too bad. So when I square, just PEMDAS, when I square this square root, the square and the square root cancel each other out. So I'm going to have 2 times x plus 1 over 2, and then minus 1. Simplifying that, 2 times x plus 1 over 2, the 2's cancel out, so I have x plus 1, and then minus 1, and that is indeed equal to x. Okay, so f of g of x equals the identity function, equals x. Now let's see if g of f of x is also equal to x. this time I'm going to put f into g. Okay, so g is the square root of x plus 1, so that's going to be 2x squared minus 1 plus 1 all over 2. So I basically took this function right here and put it into this one for x. So let's simplify that a little bit. Let's go ahead and simplify inside here. So that's going to give me the square root of, the parentheses, I guess I really didn't need them. That's just going to give me 2x squared minus 1 plus 1 just gives me 2x squared over 2. The 2's will cancel out, so I have the square root of x squared, which is equal to x. So g of f of x also equals x. Since both compositions equal the identity function, yes, these two functions are indeed inverses of each other. So in this section we took a look at inverse functions and relations, how to graph them, how to determine if two functions are inverses of each other.